Afternoon or evening or morning, whenever you're watching this, to our dearest lecturers, our dearest tutors, and all my subscribers. Today we will be talking about a computer systems project, which is about automated agricultural system. So let me introduce the topic here. Agriculture has been a key to success and widespread development of humanity since its advent in 12,000 BC, and that means it's around 14,025 years old. And with an article stating that it's the mother of invention because without agriculture, humanity will be stuck in hunter gathering cultures and civilization would have been pretty slow. So, with its invention in days gone by, there is a need to make it simpler over time, such as using shovels, wheelbarrows, and of course, nowadays we got tractors and harvesters that do everything for us. So agriculture has come so far, and the 21st century tools have become more and more sophisticated. Now we have integrated machinery inside. So now we have achieved what is called smart farming. So what is smart farming? Well, Shanimov in its journal it said that it's a range of technological advancements in conventional agriculture, which focuses on the optimization of food production and enhancement of crop quality, which can be summarized as meaning getting more food from your farmland. The rise of these technologies are also due to multiple factors, including but not limited to climate change, increasing population and food demands, and also a lack of transparency between the producer and the consumer. What this means is that because of climate change, there are places where it's too hot or too cold for farms to grow, or there is an increasing population and thus more mouths to feed, and there's a lack of transparency between the farmer and the producer, and so you don't know what's happening in between. So with this, smart farming will be aimed to reduce and mitigate concurrent issues by mechanizing the system on a commercial scale so that efficiency in food production and quality can be achieved. So what's the background? We have researched across the land and found 5 common automation functions that every single agriculture system should have, at least to be self-sufficient. First things first will be soil management, which is defined as monitoring the soil health and quality, which can include humidity, nutrient level, and pH. So it will react accordingly by adding fertilizers or increasing irrigation. This is often paired with crop management and automated irrigation systems. Makes sense because it needs to irrigate and also check if the crops need something from the soil. To manage the soil is to keep track of soil properties such as its fertility and maintain its role as a foundation for humans to grow abundant and quality crops. With that, I can move on to crop management, which is to monitor crops at real time by increasing production, saving energy, and decreasing the product loss. This is in their Enviro channel, often paired with soil management and pest control. So this good automated agricultural system can manage crop yields, growth, and diseases such as using deep learning to identify visible symptoms. What it is trying to do is to check whether the soil is giving enough for the crops and whether or not crops have been given a disease, for example, by fungal rot or by bacterial infections. They are very common and they cause a lot of failed harvests around the world. With crop management also comes automated irrigation in case the crops needed water. So automated irrigation is a device or system capable of detecting requirements for irrigation and opening or closing pumps automatically as needed by the soil or the crops. This is usually connected to soil monitoring sensors so that whatever is happening in the soil and in the crops, they can update and cause the irrigation system to fill up with the butter pumps or something. This can be done automatically or using a timer or a soil humidity sensor, but of course, user interface or user manual can also be integrated. Next one, when the crops are ripe, you need to harvest it. So machinery which can automatically harvest crops with minimal or no user presence. That's what automated harvesting is. So these devices are usually equipped with optical sensors to detect the ripeness of crops and harvest the ones that have fulfilled a certain quota. Sometimes harvesters are often equipped with many functions to suction, grasp, or pull crops from the plants. This can also include shears, for example, for apples to cut it from the branch, or something softer like graspers or suckers to get grapes from the vines, or of course something like pullers to gather berries. There are many different types of harvesters, and it depends on what kind of crops they want to yield. Next one and last one will be pest management, which functions to deter, and exterminate unwanted vermin which can potentially damage the crops and reduce quality and quantity of harvest. So similar to automated harvesting function, it's also have optical sensors which will trigger either pesticide or herbicide sprays as well as loud noises to scare the insects or other pests away. There's one that is created by a university in Indonesia which will create a 40 hertz wave to deter insects from rice crops. There are multiple more instances of these functions that are not discussed in this report, but the ideal automatic agricultural system, which will have everything to feed the increasing demand for food, clothing, and other human needs that come from plants. Thus, we can move on to market-ready products and systems. So they are expected to have multiple companies, organizations, universities, governments, and individuals which have developed farming systems with minimal user input. I can't be the only person who have made this, obviously. So below are some examples. We have Easy Farming Smart House, which sells greenhouses with multiple sensors, each coupled with multiple controllers, and IoT systems which are able to gather data from the surrounding environment. Multiple sensors are ingrained in parts of the soil and sometimes in the crops, and the internet to control aspects of the greenhouse to suit the needs of the plants. For example, grapevines need some more sunlight, apples need more water, or maybe rice needs a lot more water actually. Well, such as luminosity, temperature, and soil content. That is the technical term for this one. Of course, there are also cooling fans or heating vents in case they need to be hotter, which are connected to the system, as well as opening or closing shades required for the crops. In Europe, there's also two agricultural engineers that started FarmWise in 2016, which released a host of products capable of reducing manpower needed and increasing farmland productivity. In 2020, they released the Titan FT35, which is a weed killer, which is able to detect and remove weeds at the rate of half a second. They have a firm belief that robotics believe in agriculture and develop this to help with crop yields in the winter. And using AI as well as machine learning specifically, Titan is able to discern between weeds and crops where the wheels can go as to not trample them, and a mechanical arm which removes weeds as seen fit. I want to update you guys. There are upgrades to Titan FT35, and some of them have sensors to detect the soil, which will integrate it with the herbicides to kill the plants or weeds more effectively. Lastly, we have Surthon, which is a Dutch agri-tech company that specializes in building modern greenhouses. In 2024, they collaborated with an automatic technology company called Denso to develop an autonomous harvest that harvests cherry truss tomatoes in greenhouses. It operates 24/7, advanced vision technology to detect ripe tomatoes and cut them, as well as sensing technology, which is used to detect obstacles and let it switch lanes safely, as seen in the image on the right. Of course, there are also automation functions that are just one function. These are examples of existing products that can exist as self-contained systems for each function. Firstly, for soil management, you have advanced tech soil health monitoring, 2-year Zigbee wireless, and a local one here is HoboNet Theros 21 soil water potential and temp sensor, even though these are just actually sensors. But some of them are also equipped with actuators which can spray the plants with water if needed. So common sensors and actuators needed are moisture sensor and temperature sensor. Added here is supposed to be a spray or a pump of water, which is a segue to automated irrigation, which includes the both Netafim Dream irrigation and NetaJet 4G, and also Irrigatia greenhouse irrigation system. Some common sensors are soil moisture sensor, pressure sensor, and of course the water pump. Crop management has Farmanaut crop health monitoring, TopCon crop spec, and crop analytica. Some common sensors and actuators include the optical canopy sensor, integrated multispectral sensor, and application valves such as fertilizers, pesticides, and for other treatments. Some of them also include a water pump, as for, of course. Now to automated harvesting, we have FF Robotics, robotic fruit harvester, which is specifically for apples and strawberries usually, an Agrobot bug vacuum, which is smaller, and Monash apple retrieving system, or MARS, obviously for apples. These usually have proximity sensors and a robotic arm, though some of them also have a vacuum and a drive motor or any kind of way of mobility. Lastly, we have pest management. The existing products that we have are Solix AG Robotics, X Machines X100, and ACFR RIPA. RIPA stands for Robot for Intelligent Perception and Precision Application. Some common sensors that they have are environmental sensors, which are soil sensors, oxygen sensors, and infrared sensors, camera or vision, and as well as precision spraying so that they don't kill other bugs or plants. And of course, a way to move around, which is mobility, such as drive motor and wheels. Now we will move on to the second part of the portion, which is the logic gates. Yes. So this is the automated irrigation. So we have a moisture sensor and temperature sensor. This is for the soil. If it detects that that the moisture is lacking and the temperature sensor is also lacking, it will activate the sprinkler. However, if they sense that it has been raining, sprinkler will not turn on because it has been because it's been sprinkled by nature. However, if the moisture sensor senses everything's okay and temperature is also okay, it will also not turn on because it has rained, obviously. Let's move on to the next one. The logic equation for automated irrigation will be negation R for M plus T equals to S. Next one is the soil management, which will be opened shortly. All right, so the MPK sensor, moisture sensor, pH sensor, and conductivity sensor, and temperature sensor here. So for soil management, there will be a moisture sensor, pH sensor, and conductivity sensor. If these turn on, that means there is something wrong with it. But if they sense that it has been given nutrients, it will not turn on because the fertilizer injector should not fertilize something that is already fertilized. But if it's not, it will turn on. Meanwhile, they're also connected to the temperature sensor here, and only when there are OR gates here, then it will turn on the water pump. If they sense everything is A-OK, then the water pump will not turn on. So now let's move on to the logic equation for this, which is, well, you can see it here. Next one will be crop management, which I will cover shortly. All right, so back to crop management here. We have two guests that are returning, temperature sensor and moisture sensor. Oh, never mind. These are actually for the plants itself. Meanwhile, the oxygen and conductivity sensor is a returning guest for the soil. And there's also optical sensor, which will detect directly if the plants need something. So let's, for example, turn on this temperature sensor. It senses something wrong. Moisture sensor also senses something wrong. If the optical sensor sees nothing wrong, the water pump will not turn on. But see what happens if I press this. As you can see, water pump will also turn on because I also put oxygen sensor turn on, means something wrong. The fertilizer pump also turn on. And if they detect nothing else wrong, it will turn off. If there's nothing wrong with the conductivity or oxygen, it will also turn off, but only for one function here, one actuator. So this optical sensor is for both the water pump and fertilizer pump, but it also depends on the two sensors that are connected to either the crop or the soil. So now let's move on to the last part, automated pest control. As you can see, the logic equation is right there. Move on to automated pest control. We have an optical sensor which sees the pests, an infrared sensor which will detect the pest's heat. If they sense either of these, the pesticide will turn on. Either of these. And for herbicide, it will also sense the moisture sensor here. If they see nothing, the herbicide pump will not turn on. But if they sense something, or the infrared sensor senses something wrong, then they will turn on. Pesticide pump will also turn on just in case that there are pests around, especially underground. As you can see, they have a much more understandable logic equation of O plus I equals to HP, or O plus I equals to PP. PP is the pesticide pump, HP is the herbicide pump. And the others should be straightforward. Now let's talk about the combined logic, which we covered next part. This time it's the part 3, which is combined logic. So here you have the individual system logic design with all the 5 functions combined into one precision agricultural system. You have all the sensors here on the left and all the actuators, which are the pumps usually, on the right, except for one mechanical arm. Here we also have manual switches so that users can also manually override the system to probably harvest themselves or pump themselves, who knows. As you can see, if you have noticed here, one of the herbicide pumps are gone because we want to focus on pest management. And also, if you have noticed that the irrigation system is gone, it has been integrated into the crop management as well as the soil management as well. So let's move on to the soil management here. So irrigation and soil management functions are integrated into the crop management because they share the same circuit, which is the water pump and the sprinkler. It will also function with the harvester function with an optical sensor, modified with the manual switch. On to crop management as well, same thing. Water pump and sprinkler and fertilizer pump to be manually switched off if needed for certain tasks, such as manually spraying certain amounts of water or fertilizer onto the crops. There is now a harvester which will share a sensor with soil management function, added a manual switch for the mechanical arm, where the mechanical arm of the robot can be turned off if the farmer wanted to harvest manually. Last one, of course, is the pest management. It requires the temperature sensor from the irrigation function to be turned on, and it also added a manual switch for the pesticide pump to be turned off because in certain situation, it will either add or reduce more pesticide in certain areas. So this is an example of the pest management turned on, and this is a manual switch on. As you can see, even if the post pest optical sensor and infrared sensor is on, the pesticide pump is off because there's a manual switch turned on for the user to manually spray pesticides. And that is all for the part 3. I will now give it to Marcus for part 4, which is the mock code of how this system will go through the AI of the system, basically. Thank you away.
I'm Marcus. I wanted to show you on part 4 for computer systems, the coding part. So, I have created multiple abstract. As we know, we need to actually make our system for in real situations, our agro system would be extensible. So you can think of it as an add-on. So we have state event, state listener, component, sensor, actuator, self-contained system, and agro system. So for example, sensors, we actually can reuse the class to actually create temperature sensor, humidity sensor, rain sensor, oxygen sensor, conductivity sensor, pH sensor, optical sensor, infrared sensor, gas sensor, and test optical sensor. And now next, we also have abstracts for actuator. So to list it out, we have water pump, pesticide pump, mechanical arm, fertilizer pump, and fertilizer pump. So from here, we actually have, as we know, sensors and actuators will be contained in a self-contained system. We have multiple self-contained system, three of them, such as crop management system, pest management system, and harvester system. So in these three self-contained systems, we have their own actuators and sensors, which will work together in agro system, which is our core system. So to show you how it looks like, we have we can actually set up values first, and we can actually set up our subsystems inside operation type, and then after that we actually register them. We add observers so that we can listen to their details, try it out, and this will simulate our farming system in the interval of 5 seconds. So to show you how abstract looks like, we have all these commented code commented as well in order for more clarification. So we also have additional one which to show we have logging listener, debug listener, and alert listener. Um, After that, now let's run the code. We're gonna clear this up first, and now to show you how it works in an interval of 5 second simulation, we go to our main.py and then we play. Now we can see that uh, we can see the values coming out from each subsystems, and we can also see the fertilization pump. We can also see the irrigation pump. So as we can see, process has already started and field 1 corps is currently watering. So this is a stop order for fertilization so that it doesn't, let's just say, clash together. So as we can see, we can see it in live that currently is spraying pesticide, and if there is and if pest is detected, it will spray. And we can also see that irrigation pump is on and fertilization is on. However, uh, harvesting conditions is not met, so it is ignored. So this is how it works in action, and that's about it from me. I will stop the code now. Thank you for listening.
Thank you, Marcus. And now to conclude, as a catalyst for human civilization, agriculture is one of the first and greatest advancements of the species. So, it should also be paramount that agriculture is to be automated using real world fundamental technology to improve its productivity as the global population and demand increases every year. With the five core functions, the future of unmanned agricultural systems can be realized. To conclude, integrating digitalization to agriculture, the core advancement of the past for the present world, shall likewise become the same core advancement of the present for the future world. Here are the references to conclude, and of course, our appendices. And with that, I bid you all farewell. Thank you.